Welcome back. This is part 1, or maybe part 0, depending on how you want to start counting, in a series about the tile layers. There will be at least 2 parts, and possibly more, depending on how far we want to take this. I want to start by saying the tile layers are far from complete, but it's all in a feature freeze right now. I'm sure regular viewers of this channel are tired of hearing me say how everything is being moved to Vulkan. This means a lot of the work that's already been done will have to be refactored in the near future. The tile layers are in a working state, but there's still a lot left to do. The problem is that finishing them under the current system would be a wasted effort. Too much of it is going to have to be done in a radically different way using Vulkan. The good news is, a lot of what I want to do will actually be easier at that time, at least in theory. It will definitely perform a whole lot better at any rate. So right now, I'm resisting the urge to finish features that would only have to be scrapped or rewritten. Still, I figured it's worth talking about the tile layers as they stand right now. It'll help show off what they are currently capable of, and hopefully give a sneak peek at what they'll be able to do in the future. Before I get started on that, I'd like to talk a little about the history of tiles in video games, and how classic systems handled them. A lot of arcade machines had entire chips and dedicated ROM space for tile layers. Parallax and lots of color layers were common in arcades. But when it came to home consoles, these systems were typically scaled down to save on costs. The systems like the NES and TurboGrafx-16 could fake parallax with special tricks, like tracking the raster beam and switching out or modifying graphics data at very specific times. But truth be told, they really only had one playfield made up of character cells, known as name tables, which had to be carefully managed in order to make the most out of them. The Super Nintendo and Sega Genesis actually had slightly more advanced hardware. They had separate memory space for different layers and more room on the cartridges, and were capable of using more colors per tile. Systems like PCs with VGA and the Amiga's OCS and ECS chipsets took a different approach. VGA offered a raw frame buffer, and clever routines were used to create backgrounds with brute force. The Amiga had to use the blitter chip to copy large chunks of graphics data around to simulate backgrounds. The Amiga did have the ability to work in 2 different overlapping playfields, not counting the sprites, but using those playfields often meant sacrificing the maximum amount of colors that you could use on the screen at one time. Then you had systems like the Neo Geo, which actually had no backgrounds at all. SNK decided to forego all pretense of backgrounds and just opt for a whole crap ton of sprites. Sprites, sprites, sprites. So many sprites. In fact, you could cover the screen entirely with sprites to make backgrounds with parallax, and at the end of it all, you still had plenty of sprites for players and enemy objects. Things started looking better as systems received more video memory, faster fill rates, and the ability to work with full screen bitmaps very quickly. However, with that added power came added complexity. Fast forward to today, where we have lots of video memory, highly parallel systems, and very in-depth game engines that do a lot of the heavy lifting for the game designer. What we don't have is a very simple, low-level way to interact directly with virtual hardware that behaves like the custom chips we used to have. Sure, there's nothing stopping someone from writing games for older hardware. In fact, indie games regularly target classic systems. Some try very hard to create games that look like the games we had on classic systems, but they end up creating monstrously large applications that might look like retro games, but they actually require more power than a 1990s supercomputer had. Which brings us to modern hardware. GPUs on systems these days are not only different from classic game consoles, obviously, they're even a far cry from the early desktop graphics cards. CGA and VGA look nothing like the very first 3D accelerator cards. We've gone from fixed function pipelines to fully programmable ones and have stepped through many iterations of graphic APIs along the way. Immediate mode is dead, everything is retained. Nowadays, when it comes to graphics programming, you have 2 choices. The easy option, and probably the most sane, is to use a game engine. All of the low-level stuff has been taken care of for you, and if you want to get fancy with shaders, you can open up a whole world of possibilities. Some people choose the other option. They don't want to be tied into a game engine and would rather make their games without an engine at all. In fact, a lot of experts say, if you're not going to use an engine, just write your game without one. Use tools that already exist. It is not recommended for most people to set out to write their own engine because it can be overwhelming and it just keeps you from working on your game. This is probably really great advice, so naturally, I'm ignoring it. If you do decide to write a game without an engine, 2 libraries come to mind as some of the best you can turn to. SDL is a solid and popular choice. Another wonderful project is RISC-V. I can't say enough good things about RISC-V. If you're doing any graphics programming at all, no matter what your goals are, you owe it to yourself to check it out. It's easy to use and it does quite a bit. It's so good, in fact, that I was just prototyping some simple ideas for Fuselage and ended up writing the entire text, sprite, and tile layers on top of it. I got carried away. I never meant to use a framework. Not at all. RISC-V is just that much of a joy to use. And that's where we stand today. Fuselage was supposed to be bare metal from the beginning. It's meant to be self-contained, no host dependencies, no middleware, and the idea is this. What if an emulator existed for a console that never existed? A system with a fixed memory layout, deterministic behavior, defined capabilities. Games built for that system could run the same on every modern platform where that virtual machine is hosted. Think of the games you've played on modern PCs that could have been made for the Sega Saturn, PlayStation 1, Atari Jaguar, or CD32. Think of games like Shovel Knight, Stardew Valley, Celeste, Pizza Tower, and Balatro. Ask yourself, how many of these games could have been on older systems? How many need the extra memory offered by modern machines? Then start thinking about games that fall somewhere between what would have been possible back then, but are only possible thanks to the power of modern systems. If we have a fixed profile virtual machine, we could build low resource, no nonsense, high performance, DRM-free games that load from a single file, run offline, and just work. No spyware, no live services, no 80 gig updates, just the game, and that's what the Fuselage vision is for. In Fuselage, tiles act as the canvas of our game worlds. We build 2D environments by combining tiny chunks of graphics over and over. It's a tried and true technique that dates back to the first colored pixels. Modern day systems use textures to pull this off, and the textures are often true color modes and they can take up quite a bit of memory. For our purposes, we'll be intentionally limiting the colors per tile. In the current implementation, we're packing 2 pixels into a single byte for a total of 16 colors per tile. Technically, it's more than likely 15 since one of the colors will probably be transparent, but either way, that's 16 values. The good news is, we can have many more tiles and many more layers than we had available to us with classic game consoles. In the current form, the limit is 1024 tiles per layer, and there are currently up to 16 tile layers. When the upgrade to Vulkan is complete, I will profile much higher numbers to test for memory usage and performance, but even as things are using RISC-V right now, I'm still seeing promising results. In fact, it's probably already good enough, but things will just get better. So now we're at the part of the video you're really here to see, the Fuselage tile layers themselves. Let's look at a few functions and I'll explain their usage, their limitations, and how things will improve after the Vulkan upgrade. The first function we need to look at is init tile map. Much like the text layer and sprite layer had to be set up, so does each tile layer that we're going to use. This is the prototype for the function. As you can see, it returns a Boolean value indicating success or failure. I can't think of any reason why it should ever fail unless you just don't have enough video memory, but considering how little memory is being used for this function, that should never be an issue. Inside this function, an atlas is being created for all of the bitmaps and storage for the map itself is being allocated. We start by declaring which of our layers we're initializing, how many characters wide and tall it will be, the size of the tiles themselves, how many tile bitmaps we want to create room for, and what the scale of this layer will be. Currently, the tile size needs to be 32 by 32, since an oversight on my part has left the ability to accept tiles of any other size unimplemented. After we receive a success from the init function, we need to specify a few extra settings. One setting is the viewport, which dictates how much of the screen we want our tile layer to cover. By default, provided you have made it large enough, it will cover the entire display and even possibly extend out beyond the right side and the bottom. But we can limit how much of the screen is covered by the layer with set tile viewport. Once again, we look for a returned value of true. This function issues the command to a specific layer, and our viewport needs to be smaller than the size of the viewport we initialized. The first 2 shorts are the X and Y position and the tile sizes that the layer will be displayed at. While we're currently using tile sizes right now, this is going to change to pixel coordinates after the upgrade to Vulkan. But for now, it dictates the position based on the tile size of the layer. The next 2 values are also in tile sizes. So if these were set to 20 and 8, you would get 20 tiles across and 8 tiles down. In the future, this will be able to be set as either pixel or absolute tile sizes. But we're just going to go ahead and kick that back to the to-do list in Vulkan. The next function sets our wrapping options. This function won't matter for our purposes right now, but it will matter when we start playing with scrolling. Right now, we're just going to turn wrapping off with set tile map wrapping. Nothing gets returned by this function, but we give it the number of the tile layer we're setting, and we set the wrapping for both X and Y directions, each in their own true or false value. With wrapping off, a map can only scroll to the edge before it stops. Also, a map with wrapping on, which happens to be smaller than the tile layer itself, will fill the extra space by repeating the map over and over again. If you want to fill an entire screen with just one single tile, it would be possible to set up a tile layer that covered the whole screen, then set up a map that is just one tile high and wide. Then, whatever tile you placed inside that single cell would just repeat in both directions. It's not hard to imagine scenarios where this could be useful, and it would use only a few bytes plus the space needed for the bitmap itself. The next useful function we will need to use isn't exclusively from the tile layer. It's actually from the color system. I'm not too sure that the name I've given it was the right choice, so it may change in the future, but for now we're going to use load palette from sprite. Also used in our Hello Sprites video, this function simply takes a palette in the color struct format and loads it into the fuselage palette system. Whichever palette your tile was created with should probably be loaded here. We then use the set tile palette and assign tile functions. They must be used in that order, otherwise the changes made to set tile palette won't be reflected in the atlas. This will change under Vulkan, as the coloring will be done at frame generation by the shaders. For now, it is crucial that the tile palette be set before the tile assignment happens, otherwise your tile will either be in the wrong color or completely invisible. We set this palette by declaring which layer, which tile, and which palette to use. We then assign the tile with the layer, the tile ID, and finally the bitmap used for the tile assignment. For now, if we want to use the same bitmap in multiple colors, it must take up more than one space on the atlas. We must assign it to a tile for each palette with which it will be drawn. In Vulkan, we'll assign the tile exactly once, and each location in the tile map will have its own color entry. The effect of this will be that once we're using Vulkan, we can change the bitmap or color of any or all tiles every frame by simply changing the assignments. The effects will be instantly visible in the following frame. For now, just keep in mind that every frame will be drawn with the contents of the last Atlas update. And now we're ready to populate our map with the tiles that will make up our display. This is done using the place tile in map function. Again, we start by declaring the layer, the X and Y coordinates of the specific cells we are populating, and the tile ID that will be filling that cell. In the future, this is actually where we will be providing a palette entry to accompany the tile, so this function will be gaining an additional parameter. For now, our tiles are placed in the atlas already in color. Just know that this is one of the changes that will happen eventually. In practice, helper functions will be written which will perform all of these tasks in batches. As tools are created which will make creating and exporting maps easier, easily importing structs and other collections of data will also become available, which can automate a lot of these tasks. Fuselage is meant to be a low-level set of primitives, so knowing what's happening step by step will come in handy. In our Sausages of the Night demo, I've created two functions so far to populate the title screen. This is one such function. As Fuselage matures, a lot of this work will be automated away, leaving the need to mess with any of these details to special edge cases or situations where people are just doing things the hard way. As is the case with any game engine, success, failure, and adoption or abandonment are decided upon by the ease of use and the workflow provided by the toolchain. Fuselage is being built from the bottom up, and we're still in between anus and buttocks, so it doesn't get any lower than where we are right now. If you've managed to stick around this far in the video, you finally get to see how this all comes together. Really, it's a lot of work for a display that is nothing more than a super basic menu that doesn't really do anything. We could have saved a lot of time by simply splashing a texture on the screen and made the menu with Raylib's text functions, but we're not doing things the easy way, are we? No, we're not. So, as an extra bonus, I made a little toy that I'm going to show off that really screws with the tile maps. With a simple function, I was able to repopulate the maps with random tiles and create a display that looks like a Nintendo cartridge somebody needs to blow into. With a little imagination, it should be easy for you to think of many different scenarios where you can write into your tile maps and perform tasks like lowering drawbridges, animating fireplaces, creating flowing water, or turning a castle into smoldering ruins. I like to keep my videos short, and this one has already run longer than usual, so I'll wrap it up here. In the next part of this series, I'm going to make an actual scrolling level and we'll explore some more features of the tile layer. After that, who knows? I can't spend forever on this project though. Sausages of the Night was only intended as a demonstration, and Fuselage is a very ambitious project. I can work on one or the other, and right now, the graphics device minimalist framework is a top priority. Getting it in a usable state will allow me to move away from Raylib and start focusing on other parts of the system. So, that's all I have for now. Until next time, wash your sausages down with plenty of beer, try not to get your game controllers too greasy, and I will see you next time.